Nuclear energy is a huge part of our society, and nuclear energy has been touted at times in the past and the present as being a real cool method to get a lot of energy. And we're a hungry society for energy, all right? We need the energy for cars, we need the energy for making aluminum things and making cell phones, computers, stuff like that. Even AI needs a lot of energy to make it happen. So, one thing that people think about a lot is what's called transmutation, which is converting one nucleus into the other. And this will only happen if you have a process called fusion or fission. So first, we're going to talk about nuclear fusion. And nuclear fusion involves two smaller nuclei. So hydrogen, helium, lithium, maybe something like that. And they will essentially smash into each other, but so powerful that they actually create new atoms, which is just amazing. And sometimes a neutron will get kicked out or something like that. But the energy output is just phenomenal, all right? So in the reaction shown there at the bottom with deuterium, hydrogen 2, and tritium, hydrogen 3, you make essentially an alpha particle, helium 4, and a neutron, but the energy that comes out, minus 1.7 times 10 to the ninth kilojoules per mole. It's just fantastic. The nice thing about nuclear fusion is that the products are very clean, you have a lot of energy, there's no meltdown, as we'll talk about with fission here in a little bit. However, to make fusion happen, you have to have plasma. Plasma is a fourth state of matter we'll talk about. You need really high temperatures. It's very hard to sustain plasma and to sustain nuclear fusion, although it's coming. All right, I really believe it's coming. So in the lower right-hand corner is an example of what's called a tokamak reactor. That's a place where if you imagine the plasma kind of circles around, and that allows then the nuclei to smash into each other to create the nuclear fusion. But it's not an easy process, although the technology is getting there, and I sure hope that one day we all have nuclear fusion as our primary energy source. Plasma is another state of matter, and we've spent a lot of time this quarter talking about gases and then solids and liquids, as you know. Those are the phases of matter which are most common on the Earth. But plasma, when you think about the whole universe, is actually more common than anything, so we should talk about it. Plasma is described as an electrically conducting fluid, all right? And the fluid will flow like all other things. However, the ions are just kind of roaming around. The electrons are different, separated from the protons and the nuclei. You need a really strong magnet to keep it together, electric fields, and it's very, very hot, all right, just incredibly hot. Now, it's rare on the Earth, but in the universe, it's really common. So sometimes people call the islands like Earth to be a lot different than the rest of the universe. The sun is basically a big plasma source, and the sun is much more massive than all the other planets combined, so that's why plasmas are definitely the number one type of matter, if you will, in the universe. Remember that in space, all right, diamonds are actually pretty common and wood is rare. And in space, plasma is very common, but solids, liquids, and gases are relatively rare. So it just kind of shows the perspective of the Earth versus the rest of space, which is kind of a cool thing to think about in the back of your mind. This graph shows different sources of plasma, and again, in the upper right-hand corner, you've got the fusion of the sun, solar cores, all that kind of stuff, lots and lots and lots of plasma. However, if you've ever seen an eclipse, the corona around an eclipse, that's plasma, all right? It's plasma around the sun, but we can see it, which is really cool. Fluorescent lights use a form of plasma. Lightning involves plasma being created, which is really cool. So there is plasma around us all the time.
There's a match head. Yes. Nice.
This video was created by two of my students in 2010, and they're wonderful people, and I respect them so much. And they're in medical school; they're doing great things. But anyway, at the time, I said, "Oh well, plasma is really difficult to create and stuff like that. You need high energy and stuff like that." And they said, "Hey, what about the grape experiment in their microwave?" And I'm like, "What?" So anyway, these guys put a grape in their microwave with a match head, you can see, and when they turned the microwave on, this really bright light occurred, and I thought, no way, this isn't plasma, which is what they claimed it is. Well, I did some research, and I'm not convinced that it's not plasma. Okay, I'm not going to say I totally believe it's plasma. I still think it's some kind of reaction, maybe with the match head, but I can't totally kick out based on the research I did that it isn't plasma. So maybe you just saw plasma created in a microwave, and you can try this experiment too. I take no responsibility for any damage to your microwave because again, plasma is a super high energy source, and I keep nervous. But they did it several times and made this video for me. So my hat's off to him. This has given me a lot of things to think about. It very well might be plasma. I can't totally say it's plasma, but I certainly can't say it's not plasma, which is where I started this whole research part. So again, my hat's off to them. And if you see a way to make plasma, you let me know as well.
Tokamak reactor is used to basically create the magnetic fields and control the heat that's necessary for making plasma. It's kind of like a donut, all right? And in the donut, then you have the different ions running around and around and around and around, and that's what allows the plasma to start happening. And again, this is not something you can do in your garage, at least not yet anyway. You need some pretty strong kind of protective currents in order to protect you and everything else around it. This is a video I was able to obtain from February of 2022. In the United Kingdom, they're creating this kind of thing, and it shows the actual tokamak reactor with the plasma running around, which is just amazing. But anyway, they were able to create more energy than they put in, 59 megajoules. So that would be 59 times 10 to the 6 joules, which is really, really cool. So come on, go, go, go. Anyway, so one day, hopefully this will be more possible, but we'll see what happens, of course. This picture shows the inside and outside views of the tokamak reactor. I think this was from Germany, but I'm not totally sure. Anyway, there's a person standing inside the tokamak reactor for scale comparison. And again, when the actual plasma is running around, this person would not be there, of course, but it's kind of cool. But outside, my goodness, this is an engineering marvel that it's able to even be constructed, because you have all these different kinds of electricity and cooling and heating and blah, blah, blah. It's amazing. But anyway, one day, I'm hoping this will be our primary energy source. So, for example, hydroelectric is what Oregon uses a lot, but hydroelectric has been controversial. It causes lands to be flooded and fishing areas to be messed up, stuff like that. Of course, I love solar power, the energies and stuff like wind power, but people sometimes don't like those. Oil and gas, of course, have been traditional powers that people have used. But fusion, man, if you could just make it, it would be so clean. I think it would be super cool, but, you know, what can you do?
In the nuclear fission of uranium-235, a neutron collides with a uranium atom, causing it to fission into two smaller nuclei. On the average, 3 neutrons are emitted for every U-235 atom that divides.
When people hear nuclear power, they usually are thinking of nuclear fission, and fission is different than fusion, okay? While fusion involved lighter nuclei becoming heavier, fission involves bigger nuclei becoming smaller. And usually what happens is you have a big element like that uranium-235, big here meaning lots of protons and lots of neutrons, and they essentially fire a neutron into it. It breaks up the bigger atom, and in this case it creates a krypton-91, a barium-142, and 3 neutrons, and you create lots of energy in the process, which is really cool. Now, about 17% of the world's energy is from fission. France is the leader. They have an incredible amount of nuclear fission reactors. I consider what France has done to be pretty cool. They're using some of the waste and recycling it, but you do need a neutron trigger, and you must keep these under control, as we'll see.
If the mass of U-235 is less than the critical mass, no chain reaction will result. Most of the neutrons will escape to the surroundings. If the mass is critical, most of the neutrons will be captured by other U-235 atoms, and an uncontrollable chain reaction will occur. This is the explosion of a thermonuclear bomb.
Now, nuclear fission does create a lot of energy, and the technology is more or less available to us right now for using nuclear fission. But there are some problems, all right? So, first of all, let's talk about the waste. When you have nuclear fission, you make smaller nuclei, but it's not like helium and stuff like that that's easy to control. You're going to have some really bad kind of radioactive wastes around. So, when it comes to nuclear fission, you have to think about what you're going to do with the waste. And what people have usually done is they've buried it in a big hole or something like that and just said, do not come back for 2,000 years or whatever. And the half-lives are crazy, but that's another thing. So the waste particles must be considered. France has done a great job in recycling a lot of the waste, which really impresses me, by the way, which is pretty cool. Another thing that's really important to realize is that nuclear fission can result in nuclear explosions, all right? Fusion can too, but the energy for keeping the plasma up just dies out, and so you won't really have that problem. But with fission, this is definitely something to consider. And there have been some problems, as we'll see later, with fission reactors. However, that being said, there's more than 400 nuclear fission plants in 30 different countries. The United States has about 100 of them working right now. Now, in the middle lower part, I feel it's important to talk about the Trojan nuclear power plant. This was actually a fission processed nuclear fission power plant in Oregon. It was kind of by Rainier, Oregon, in northwestern Oregon. And this picture was taken in 1973. And I visited this place. That orange building was kind of like a little OMSI. You could go in there and see all these cool displays about nuclear power, blah, blah, blah. However, it was also some problems, all right? The things that created the electricity were breaking down. There were some problems of containment, et cetera, et cetera. So one day they finally just shut down. They imploded the cooling tower, that kind of tall thing right there. And so now you wouldn't know it was even there. I think there's a park with maybe a plaque or something, but it certainly isn't what it used to be. So Oregon did try nuclear fission, but it just didn't work out for Oregon. All right. And that's what some other countries have seen too. We'll talk more about the safety of things. Anyway, in this process, though, the energy that's created basically heats water, and the water goes through several things to basically move a generator to create electricity. And that's where electricity comes from. And they would do something like this with fusion too, which is kind of cool. Pretty exciting.
Located in the nuclear core of a fission reactor are fuel rods, moderator and coolant fluid, and control rods. Each fuel rod contains tiny pellets of uranium dioxide. In these hundreds of fuel rods, fission occurs, producing an average of 2.5 neutrons per fission reaction. The fuel rods are surrounded by water, which acts as a moderator by colliding with the neutrons and slowing them to a low thermal level. The water absorbs the thermal energy, which is used to drive a steam turbine to generate electricity. The low-energy neutrons enter other fuel rods and collide with uranium-235 nuclei, creating additional fission chain reactions and the release of more neutrons. The amount of low-energy neutrons present is regulated by control rods made of boron, which are very effective at absorbing neutrons. These rods are raised out of or lowered into the core as needed to sustain the chain reaction at the desired level.
On social media, I follow several nuclear energy kind of groups and stuff, and I'm always fascinated by what they say. And truth be told, there's a lot of power when it comes to nuclear fission, all right? Because, wow, you get a lot of energy out. It can create electricity. You don't have to rely on Middle Eastern oil, which is sometimes a little politically charged and stuff like that. But again, you do have the waste, which is bad. One day, I think fusion will make the fission process not as attractive, but anyway, that's still, the technology isn't there yet. It's getting there, but it's not quite there yet. However, with nuclear fission, there's also been what are called problem events, and I want to talk about those real fast. The first problem event was actually from 1961 in Idaho Falls, Idaho, our neighbor next door. And several people, I think 3 people actually died as the result of a nuclear reactor problem they had. And they kind of hushed this up. I just found out about this not too long ago. If history is your thing, you might find that interesting. However, in 1979 was 3 Mile Island, which was a series of nuclear fission plants in Pennsylvania. And they definitely evacuated a lot of people. They thought it was going to blow, but they were able to control it and stuff in time, no problem. But it was very scary. People talked about that for a long time. What was really scary was in 1986 in the Chernobyl reactor in the Ukraine. And oh man, that one had some serious problems. There was an HBO series about this, which was just terrifying to me. Other countries weren't told about this until several days after, so it was a political nightmare as well as the nuclear radiation. That's a fascinating subject too. So Chernobyl is still heavily radiated. It's a very dangerous area. You want to be very careful. Pretty crazy. In 2011, Fukushima in Japan was another place where they had a nuclear incident. All right. There was an earthquake caused a tsunami, and the tsunami came in and wiped out lots of their nuclear power plants, and it created a lot of contamination of the whole area. Very sad, although actually the radiation from that has been less than I thought it was going to be, which is pretty cool. But again, another thing worth checking out. But what I really want to highlight here is Hanford, Washington, and we live here in Gresham right along the Columbia River. If you go upriver, kind of over by the Tri-Cities, that's where this Hanford nuclear power plant is. And part of World War II, they were developing some of the tools for their nuclear bombs in Hanford. And since then, they did lots of nuclear work. The problem with Hanford, though, is that they just put all their waste in basically a hole. And the hole is next to the Columbia, and the Columbia, the groundwater can get into the Columbia, and that water comes right down us here by Portland, Oregon, and Gresham, Oregon. So Hanford is a nuclear mess, all right? They've done some really cool science, and I love touring it. It was fascinating. It was a really, really cool thing to see how the uranium was turned into plutonium and stuff like that. However, it's definitely something that we should be concerned about as residents who live downstream of Hanford. So anyway, I'm off my soapbox, but just be a little careful when people say that fission is so cool, because maybe one day it will be, but right now there have been some problems with fission, and it makes me nervous when I do it. But fusion, on the other hand, green light, sounds cool. See what the future holds. An unsung hero of nuclear science is Lise Meitner, and she was one of the people that actually helped to explain the process of fission in 1938, which is great. And she worked with Otto Hahn, Fritz Strassmann, and Otto Frisch, and together they were the ones that came up with this idea of fission, which was fantastic. However, even though an element was named after her, element 109, meitnerium, which is a fantastic homage to her, by the way, she was also, like Marie Curie, forced to work in the basements of buildings where it was really cold and radioactive. She never got a Nobel Prize, although Otto Hahn did. He was the one that claimed that he had discovered fission, kind of kicked her out. Lise Meitner was a pacifist, and she refused to support either the Allies or the Axis in World War II. She went to Switzerland, and I think that's why she was kind of ostracized from a lot of the community. But her work is fantastic. She deserves a lot more credit than she has received. I encourage you to check her out too if you're ever curious about it.
Even some everyday objects contain radioactive sources. Let's see how a Geiger counter responds to these items. First, we look at the background reading. Listen for the rate of the counter clicks and observe the meter response. Smoke detectors use a shielded americium-241 source. Smoke detectors should never be disassembled, as has been shown here for demonstration purposes. Now we observe the response of the Geiger counter to a lantern mantle. Lantern mantles can be obtained at any sporting goods store. This brightly colored orange Fiestaware plate contains uranium oxide in the glaze. The radiation level is high enough to be dangerous if exposure is prolonged. The blue Fiestaware plate has a non-radioactive glaze.
Geiger counters are used a lot of times to detect radioactivity, and it's not too expensive to buy a Geiger counter. You can search your house and stuff like that. I don't know if I'd recommend it, but it is something that's done. Anyway, in the Geiger counter detector, there's basically a little tube, and it usually has argon gas, something inert. And when radiation comes in, it ionizes the argon. Argon doesn't usually form positive or negatives, but it will when the radiation hits it. And when the ions form, then the anode and cathode start conducting electricity electricity, and you're detecting then a radioactive incident, all right? And it can be kind of important, and there's different types and qualities of Geiger counters, but it's pretty cool. People used to use that orange Fiesta ware a lot for glassware, but it used a uranium ore that actually has measurable radioactivity on it. I would not use orange Fiesta ware for your dinnerware if I was you, but it's up to you. Anyway, the different radiations certainly can get through substances different. In the lower right-hand corner there, you see how alpha particles are stopped by just about everything because they have the most mass. Beta particles and neutrons have mass. They go through a little bit more than the bigger alpha, but they get stopped by water and metal. But gamma radiation is super hard to stop. Like we saw in that video, gamma goes through just about anything. So sometimes, honestly, with gamma radiation, it's just best to run. Get some distance between you. Let the air molecules try and absorb some of the gamma radiation and stuff if possible before it gets to you. There are lots of units for biological effects of radiation, and we're not going to go through all of them in great detail, but I would like you to hear these names. The Rontgen, which is named after the X-ray developer, is one of them. The Curie, which has the symbol C, capital C, little I, is another one. Rad, Ram, and lots of other ones. And the Rontgen is the measure of the radiation exposure proportional to air radiation, air ionization. So a chest X-ray is 0.1 Rontgen. That's kind of the idea. A REM is a Rontgen equivalent for people, for man, but it could be a woman too, not trying to be weird about that, sorry. A sievert is a newer one, but it's used a lot by the medical people. It's the health risk of ionizing radiation. It's actually an SI unit. And so on the right-hand side there is a little picture I was able to obtain from a dentist. And you can see on the top it says eating a banana. You get 0.1, microsieverts. All right, so a pretty small amount. On the other hand, the dental ones, and again, this is from a dentist's place, so it's going to be pretty positive. A dental CT scan, you get 36 microsieverts, while if you look at, say, a mammogram there, almost close to the bottom of the gray, it's 3,000 microsieverts. So it just kind of lists the different pieces and stuff and how they're available. A Curie is kind of fascinating to me. A Curie is a quantity of an isotope that undergoes 3.7 times 10 to this 10th DPS, disintegrations per second. So disintegrations per second means how many atoms are breaking down per second if it's an elemental source. Sometimes you see it decompositions per second, same thing, all right? 1 rad is equal to 1.00 times 10 to the minus 5 joules that are absorbed per gram of material. And if you happen to get a 450 rad exposure, that's an LD50 for humans. Now, LD50 is something kind of freaky to me. LD50 stands for lethal dose 50% of the time. So if you had 10 people and they all got 450 rad, half of them would die. They'd get a lethal dose, and the other half would survive. So good to know the radiation that's around us. Remember, some radiation is around us all the time. It's very normal. You want to try and lower your exposure to radiation. So if you don't need a chest X-ray, it's probably better. On the other hand, if you need a chest X-ray, you better get one because there's probably more advantages to getting the X-ray than the disadvantages of having the radiation. So here's a statement I'd like you to analyze. We should try to live as radiation-free as possible. And let's go through these and talk about them here real fast. A, yes, all radiation is bad and it's best to have no radiation exposure at all. No, all radiation is not bad. There's some good uses for radiation. The medical field definitely uses radioactive devices for lots of good information gathering. So that's not quite right. So even though I think it is good to live as radiation-free as possible, you don't want to think about all radiation is bad. So that's why answer B becomes pertinent. Yes, we gather some radiation exposure naturally due to geological processes in the Earth and from space. Some radiation exposure is natural and normal. And that's obviously the right answer here. You want to keep as much radiation away from you as possible. So in the little picture right there, don't expose yourself, I'm cracking myself up, don't expose yourself or your lab partners to radioactive powers unless you really have to. However, some radiation is okay. We do get some radiation from the Earth, like I said, all the nuclear processes happening down there. Some stuff comes from space and stuff down to us. It gets through the Earth's atmosphere. A little bit is okay. Just try not to go crazy. The other answers are just silly. We can trust the government. No comment. D, I want to be like Peter Parker, Spider-Man, who was written by Radioactive Spider. Well, that would be fun, but no, I don't think so. And the last one's about Bruce Banner, the Hulk, gamma ray burst. I have a strange sense of humor, sorry. A nuclear transformation is something where you can induce a new particle to be created by accelerating a particle and colliding it with some other nuclide. And this is a really cool kind of field. They use things like linear accelerators and cyclotrons to basically power up this one nucleus and then smash it into another. So the picture there shows a cyclotron, which has traditionally been one of the ways that they've made these heavy nuclei. And the periodic table has certainly advanced by these kind of processes. The heaviest elements that have been made, they don't exist for very long. However, if you power them up and smash them into it, you can actually make other elements happen, which is pretty exciting. These pictures here are from the Large Hadron Collider in Switzerland and CERN, and these are the most powerful, arguably, of all of the particle accelerators that are available right now. And you can see in that picture, it's just like a massive circle. They're basically accelerating these particles faster and faster and faster until finally they smash into something, and hopefully they create new pieces. They're also looking, though, at quarks and different kind of elements. It's not just making heavier elements, but it's really exciting research, and I always love to hear what comes out of CERN's information. Astronomers and chemists work together to try and figure out the origin of the different elements. And this is another big kind of thing. So in the Big Bang, they basically created hydrogen, helium, maybe a little bit of lithium. But where did all the other elements come from? And after we talked about how iron, 526, is basically the high point of making elements, where do the heaviest ones come from? Like gold is number 79. Gold is available, of course, in necklaces and jewelry and stuff like that. Where did all the gold come from? And that's a really cool question. So they have lots of different theories as to where the other elements came from. So for example, exploding white dwarfs, I love that. Merging neutron stars, whoa, cosmic ray fission. It's a fantastic field. Astrochemistry is astronomy and chemistry coming together, and I think they're doing some really cool kind of work. So anyway, this is just something that is kind of an interesting part of this field. A kilonova is when two neutron stars collide into each other, and they feel that sometimes that might be responsible for a lot of the post-iron elements on the Earth. So if you have two neutron stars, first of all, that's amazing, and if they collide into each other, that's got to be an incredible amount of energy. They feel that that might be responsible for the gold and the platinum and the other post-iron elements that were very useful to us in our bodies and in life. Selenium, number 34, is an example of that. Our bodies need a little bit of selenium to make our biological functions happen. I'm not much of a biological scientist, I apologize, but I know you need selenium, woohoo, and iodine for that matter. Again, all these post-iron elements, it's amazing that they're out there.
My main MC, Alpine Cat.
With the serendipitous B.O.B.
Mr. B, drop the beats.
As teaching is one of this lab's main themes, it's the place to introduce me to physics with beams. They accelerate nuclei, the protons and neutrons at the centers of atoms. We call them nucleons. Protons define the element, it's chemistry. Neutron numbers affect elements with subtlety. They define the isotopes, and with effort they hope to make some that no one's ever seen before, and that's dope. So you know the elements from the periodic table, but this other version highlights isotopes that are stable. The isotopes we know are on a diagonal track, and at first glance, I thought it looked pretty whack. But as you get away from that stable nucleus line, there's radioactive isotopes we don't usually find on Earth, because these nuclei prefer to decay into more stable isotopes by tossing particles away before they can. The teams here check out their dynamics, measure masses in lifetimes, and study their mechanics. They're building F-Grid with mysteries to solve, like what reactions drive stars, and how do they evolve. The strong force finds nuclei, but we still can't say exactly why some are stable while others decay. A more powerful machine can push the frontier. The physicists here, they get nuclear. So let's say you were making a new kind of nucleus in F-Grid, a plant facility that's long been discussed. The starting atoms, They're just ordinary, stable isotopes. They're easier to store and carry. You strip off their electrons for a charged state. They zip through electric fields made to accelerate. Then you slam them into something. We call it the target. 5% of your nuclei are gonna really hit it. Those that do will be different from your starting crew. They've lost protons and neutrons, or maybe gained a few. All kinds of fragments have just been created, so you put them through a magnet that can get them separated. If it's got lots of protons, it takes an inside curve, but more neutrons tend to drag it for an outside swerve. You filter out the isotopes you don't want in the stream, and voila, you got a rare isotope beam. And to put your nucleus on the nuclear map, you'll then measure it in a detector or trap. This facility is for research and to teach, so that you could be more than just a figure of speech.
Okay, this video is very fun, and it actually goes on longer, but I don't want to keep your attention that long. If you're curious to see the full video, you can see the YouTube link right there. This video comes from Michigan State University, where there's the National Superconducting Cyclotron Laboratory, and this kind of talks about a lot of the things we've looked at in this section so far. They're basically taking samples and accelerating them to just incredible energies, smashing it into the target, and 5% of them are really gonna hit it, which is what she said. I love this. Anyway, the 5% are what they're after. So they try and detect them to try and find heavier elements and stuff that haven't been seen. And you could see there, they showed briefly the peninsula of stability and the sea of instability around it. They are after, arguably, looking for those islands of stability that may be out there too. And who knows, maybe they'll find it. It's pretty cool stuff. This is a great place to do research. It always looks like there's a lot of fun going on there. If this is your thing, I encourage you to check out Michigan State University.
Suppose you've discovered an ancient bone amulet in an archaeological dig, and you want to know its age. You can use the rate of decay of carbon-14 to determine the artifact's age. The nucleus of a carbon-14 atom is unstable. At some time, this unstable nucleus will emit a high-energy electron called a beta particle, which has a 1- charge. The beta particle causes a neutron to change to a proton, and the carbon-14 atom then decays into a nitrogen-14 atom. The average time for half of a group of carbon-14 atoms to decay is 5,730 years and is called a half-life. Your bone amulet is found to contain only 12.4% of carbon-14. How old is the artifact? The level of 12.4% indicates that 3 half-lives have passed. 3 half-lives times 5,730 years is 17,190 years old. Carbon-14 samples can be accurately dated up to 60,000 years old.
Carbon-14 has been used to identify the time elapsed of certain old objects, and it's fantastic. In a nutshell, as we live, we breathe in, breathe out a lot of carbon and nitrogen and stuff like that. But along the way, some of the nitrogen ends up creating a carbon-14. Now, normally as we live and breathe, the carbon-14 is exhaled and stuff, and we don't have to worry about it. But once a person is dead, then that exhalation part, if you will, doesn't exist. So the carbon-14 amount at the time of passing is a constant, and then you can measure how much carbon-14 is left over time using these kind of half-life systems. So carbon-14 has a half-life of 5,730 years. So if you measure the amount of carbon-14, then you can measure approximately how old it is. And it works really well up to 60,000 years old. However, it doesn't work super well up until about from 1900 to the present. The Industrial Revolution apparently has created so much carbon that it kind of messes with figures, apparently. But the older things are great. Now, this is radiocarbon, but this is actually a big field. It's radionuclide dating, and there's more than just carbon out there. There's other isotopes that can be studied. So it's a fantastic field, lots of potential for figuring out how old things are. Pretty cool.
In positron emission tomography, radioactive tracers emit positively charged electrons called positrons. These positrons encounter electrons and they annihilate each other to produce 2 gamma particles. Gamma particle detection from several angles in conjunction with computer imaging produces accurate images of soft body tissues. PET is particularly useful in diagnosing Alzheimer's disease in brain tissue. Nuclear magnetic resonance imaging, or MRI, is a popular diagnostic technique because it does not submit the body to dangerous high-energy particles. MRI is performed by placing the person in a large cylinder that contains a strong magnet. The magnetic fields of the atoms of the body are caused to resonate by the introduction of radio waves. A computer interprets the signals put out by the resonating atoms to produce a two-dimensional view of the body. The MRI is especially useful in detecting abnormalities in soft body tissues.
Medicine uses nuclear chemistry in a multitude of ways, and PET, positron emission tomography, is one way. They take a molybdenum-99, and after they do some cool things to it, it ends up making a metastable technetium, that 99MTC. And then the 99MTC is in your body. It emits a little bit of energy, which can be detected in that little video thing there, and it gives really great images of inside the body, stuff like that. Pretty cool. Now, MRI doesn't involve the actual destruction of the nucleus at all. So in MRI, there's no beta particles, there's no alpha particles, gamma rays, and stuff like that. But MRI does use the nucleus, and you can excite the nucleus. We talked about in Chem 221 how an electron can go from a spin 1/2 to a spin minus 1/2. There's an equivalent kind of process in MRI for the nucleus. And through MRI, you can also get lots of cool information about what the body looks like and stuff like that. So medicine uses a lot of nuclear chemistry. Pretty exciting stuff.
After graduating from UCLA with a major in chemistry in 1934, I went to Berkeley to obtain my PhD in chemistry in 1937. And then a few years later, I became involved in the research to synthesize and identify the so-called trans-uranium elements. Uranium has the atomic number 92 and is the heaviest naturally occurring element. And what we did was go on to produce by nuclear bombardment elements with atomic numbers greater than 92. For example, 93, 94, 95, 96, and so forth. The most important one, of course, is the element with the atomic number 94, plutonium, which has the fissionable isotope that is used in atomic energy and was used in the atomic bomb that brought an end to World War II when it was used at Nagasaki. We named plutonium after the planet Pluto, just like uranium had been named after Uranus and neptunium after Neptune. We could have given it the name plutium after the root Pluto, but we like plutonium better. And we should have given it the symbol PL, but we like PU better. And we thought maybe we would be criticized for giving it that kind of a symbol. We went on, after I moved to Chicago, to work on the chemical processes for the separation of plutonium for its use in the atomic bomb, to the metallurgical laboratory of the University of Chicago. And here we went on to discover the next two elements with the atomic numbers 95 and 96. And in order to do this, we had to predict the chemical properties using the periodic table, but the form of the periodic table at that time was wrong, and I changed it and created the actinide concept for placing the heaviest elements in the periodic table. For this, I received the Nobel Prize in 1951, so that shows you how easy it is to do work that would give you a Nobel Prize. One of the elements that interests me very much that was synthesized is the element with the atomic number 106, which has been given the name by the discoverers, of which I am one, seaborgium, with the symbol SG. The Commission on Nomenclature of Inorganic Chemistry of the International Union of Pure and Applied Chemistry that have to approve this name rejected it because I'm still alive, and they could prove it. But there was such a universal disapproval of that action that it now looks like the name Seaborgium for element 106 is going to remain. And of course, I'm very pleased about that. This is a very high honor. I think it's a greater honor than even receiving the Nobel Prize, because it'll last forever. The name Seaborgium will be in the periodic table 100 years from now, 200 years, 1,000 years from now. Actually, a total of 20 transuranium elements have been synthesized since that first synthesis of element 93 and 94 in 1940 and 41. So that now we're up to element 112. And it looks like it's going to be possible as the years go on to synthesize and identify perhaps another half dozen transuranium elements. I think this will occur after I'm gone, but perhaps during the lifetimes of many of you, and perhaps some of you will be involved in the discovery of these additional transuranium elements.
Dr. Seaborg is one of my heroes in chemistry. And Dr. Seaborg, let's start right away. He went to a community college. He needed to have a scholarship to go. He came from a very poor family, but he was able to get a scholarship. He was able to make it to the community college, which is great. It was down in Los Angeles. But anyway, then he went to Berkeley. And in the Berkeley area is where he really started to shine. And he got into the creation of some of the heavier elements. And this was during World War II, the Manhattan Project. But he was helping to make some of them and stuff like that, which is cool. But he went much further than that. He went on to discover a whole bunch of different elements. I believe he has discovered more elements than anyone except for one other person that was on his group that was actually found a few, was part of the groups that discovered a few more. But he's really cool. Dr. Seaborg was the science consultant to several presidents. He was really powerful. He believed in peace. He didn't believe in war. He was just a really cool guy. And then they wanted to name an element after him, but oh my gosh, he's still alive, and to name an element after someone, you have to be dead. So there was a big controversy, but just a little bit before he passed away, then it was actually approved that Seaborgium was named after him. So he's pretty cool. Again, he is the product of community college education, and I don't think I have to understate the importance of that by any means. And Dr. Seaborg is one of the greatest scientists I think that ever lived. He was also one of the group of people that helped to make the island of stability idea. So while we're on the peninsula of stability, or the band of stability as it says right there, he was one of the people to propose that there could be these islands of stability. So pretty cool person. I think he's worth talking about. There's lots of information on him if you ever want to learn more about him. Okay, that's it for Chapter 20. I sure appreciate you being here. There are certainly some more things for you to learn the material if you'd like some more practice with them, and I encourage you to check it out. Thanks for spending your time with me. I really do appreciate it. And if you have questions on anything, let me know. Have a great day.